All right, today I want to talk about procedurally generated terrain. Back in 3.12, we saw the terrain toolkit that had a tool for generating terrain. Let me get a share screen going here. But this one's based on something by Sebastian Legue, who has a website, a YouTube channel that has lots of interesting stuff in it. It's a great place to go and look for things. And this is only one chapter out of a much larger project of generating procedural terrains. The basis of the tool is one of the built-in Unity tools, Perlin Noise. This is a pseudo-random number generator. If you want to see how Perlin Noise works, this is the place to have a look. And this tutorial shows a lot about manipulation of textures, color maps, and meshes from within a program. So Perlin Noise was developed by Ken Perlin, a professor of computer science. He's kind of unique in that I think he's probably one of the few computer scientists who ever won an Academy Award. 1997 Academy Award for Technical Achievement. And it was awarded for this algorithm. So think up an algorithm, you can win an Academy Award. One of the things that he builds in here are a number of custom editors, editors that have the ability to perform live in the editor, even when the game's not running, and that can be really cool. Things like this. Here's, we're not running, but if I change the random seed, my terrain changes. If I adjust some of these parameters, things change in real time in the editor. So the custom editor, custom editor scripts must reside in a folder called editor. And this is the script that implements a button to trigger mesh creation, as well as this live execution. So we need this using editor. This is the program or the script that we're going to access when we trigger this thing, the map generator. And we do this in the OnInspector GUI. And OnInspector GUI, way back a long time ago, we talked about the immediate mode GUI. And we said this is not the one to use in games, but we will use it when we get to editor, custom editors. And here we are in a custom editor. So it has a GUI layout button generate that triggers map generation. This is the program that we're going to access. So map generator is a map generator target. And down here we're calling map gen and a function in map generator. If we have auto update on, of course, it's going to generate the map automatically. So most of the work is done by this map generator script. It has a bunch of public variables. One of the things to note in here is the use of a slider. This makes a slider for our persistence. So that's where this comes in, this little slider here. And also for the Lacunarity also has a slider. And here we can set the range of the slider. We're also referencing a struct, a terrain type that has a name, a height, and a color. And these are accessed here as arrays of regions. And we can see this here. Here the name, the height, and color. Those are all part of this. And without this terrain type struct, we would have a much more kludged up inspector. Another obscure feature in this program is the use of the Onvalidate function. This function is called when the script is loaded or when a value is changed in the inspector, and this only works in the editor, but it checks to make sure the map width is greater than 1, otherwise it sets it to a minimum value, and it does this with all the other stuff. So that's pretty cool. Now, the generate map function that we saw called from the custom inspector when we changed something or when the button press occurred, generates an array of floats in something called the noise map. It's a 2D array, so we've got a little comma there. It generates the noise map, and it takes the width, the height, the seed, the noise scale, octaves, persistence, and lacunarity. All these things from our inspector here go into the generate noise map. We'll come back to that in a little while. The noise script that we're calling is not attached to an object. It's accessed by being in the same folder as the map generator. So here's my script, there's the map generator, and there's noise, which is not attached to an object. It's not even a mono behavior. So we want to assign colors based on the height of the generated noise map and the terrain definitions in the regions. Color maps are 1D arrays, so I make a color array, color map, width times height, and then I go through width and height, checking for the value of the noise map at locations X and Y, and assigning to that a color map from the regions. So that's picking colors out of these regions. It's just assigning one of those colors. Depending on the value of enum, we're either going to display a grayscale of the noise map or the texture that we colored by height or the terrain mesh. So this is just depending what the draw mode is. Here's the draw mode up here. Right now we're drawing mesh. There's the grayscale map. There's the color map, and here's the mesh. Just doing those different things. So we need to look at the noise, generate noise map function. We need to look at the texture generator that generates a texture from a height map. And we need the texture generator that generates a texture from a color map, as well as the generate terrain mesh. Now, none of these are mono behaviors, nor do they appear on any objects. They're accessible because they live in the same folder as the map generator. And we access various variables in here through the static variables. This is the noise class. It's the generate noise map that we called back there to generate our checkerboard of floats. Is not a mono behavior, and it's a static class so that we can access those. Generate noise map itself is a static so that we can access it from another another program, another script in the same directory. So anyway, I declare this two-dimensional array to be width by height. I have my random seed that I initialize. Having a seed means that it's reproducible. I can set a particular seed, and every time I run it, I'll get exactly the same result. That's worth having. And then I'm going to select a point to sample the Perlin noise. The Perlin noise is that grayscale cloud of bumps, and I'm going to sample that at somewhere other than its origin. So this is the X and Y offset. And then I also have an octave offset that lets me offset the different octaves. I'm going to sample this noise at different scales. I'm going to have a broad scale, then a smaller scale, and a smaller scale. And this way I'm sampling it not at the same place. I have a trap for a scale too small. I don't want it ever to be 0 because I'm going to scale my values between 0 and 1. This will be helpful when it comes time to setting grayscale maps. So I've got a minimum value and a maximum value. And for zooming purposes, I have a half width, the middle of the map. Now, the way this sampling of Perlin noise works is we have octaves. We start off with amplitude 1, frequency 1, and we go across our map, and we then step through the different octaves. For instance, over here, I have 3 different octaves. So the first octave, if I have just 1 octave, it's smooth. If I up this to 2, now I get some extra bumps. And if I up this to 3, there's more structure. And notice each time I go to a higher octave, the bumps get closer together, and the persistence is how much smaller they get as we go from 1 octave to another. In this case, they're going to be reduced by 0.36 every time we go to another octave. Lacunarity is a measure of how different the frequencies are between the octaves. So if I turn this up a lot, the higher frequency, the higher number of octaves become much shorter wavelength, shorter in frequency, or longer and shorter in frequency. So I go through this, and I set my sample positions based on that the midpoint of this thing, my frequency, my scale, my octave offsets, and I sample the Perlin noise, the mathf Perlin noise function at these different points, scale it by 2 and subtract by 1. So now that is in the range 0 to 1. Then for the next octave, I scale this by the persistence, so that makes the amplitude smaller, and I scale it by the lacunarity, so that makes the frequency bigger. Lacunarity is greater than 1 and persistence is less than 1. Finally, just to make sure that I don't have any values outside my range, I just make sure that I don't. Well, I'm catching here min and max values that I'll use for scaling, and then I store this back into the noise map X checkerboard array that is what I was building by this thing. Okay, so in order to scale this, I'm going to use an inverse LERP, and this is going to scale the min and max values to 0 to 1. So this goes through and scales min and max, scales the height between min and max, and this is what's getting scaled here. So we're setting this back. All of our values are now between 0 and 1, and we return the noise map. And that's what's being generated here in this noise map. If I go back to 1 octave, this is that Perlin noise. As I go to 2 octaves, now I have a higher frequency sampling of that same kind of black and white picture at some different position. I've got some offset here, 5 in the Y, so I'm offsetting the position that I'm grabbing. The texture generator, texture from height, takes that height map, the above noise map, and makes it a grayscale color map. The grayscale color map is a 1D array of colors. So I've got my 1D array of colors that's width times height. I go through height and width and assign basically a color that is lerped between black and white by the base of the height map. Lerp, remember, the linear interpolation between the first and the second based on the value of the third, which is between 0 and 1. And when I get done with this, I return that texture from color map. Texture from height map. So now the texture from color map takes that color map and makes a 2D texture. So I'm generating now a 2D texture. The texture itself has width and height. I'm using a point filter mode, which is non-blurry. If I set this to blurry, I would get a blurrier color map. I'm clamping so it's non-repeating, and I'm setting the color of the pixels from that color map that's passed in here and returning the texture. The mesh generator is a bit trickier. The mesh generator that we see over here that actually makes our bumpy terrain. This is actually going to build a mesh from scratch. It's going to build all the vertices, the triangles that connect the vertices, the UV maps, and so we have this mesh data that contains vertices, UVs, and triangles. These are establishing these. We have a function for adding a triangle. We have the 3 corners of the triangle, and this adds A, B, and C, and increments the triangle index by 3. And we have a function, create mesh, that basically makes a new mesh, adds in the vertices, the triangles, the UVs, and so that it's lit correctly, recalculates the normals. All that very cool. So the mesh generator takes that, the mesh generator, also not a monobehavior, note, has static mesh data for generating terrain mesh. This is the function. It has a 2-dimensional array of height map, and it sets the width by the length in the 0 dimension and the height in the length in the 1 direction. It makes a new mesh data with width and height. That's this thing. It initializes the vertex index, and then it goes through nested loops on height and width, where it's making a vertex in that vertex index. It's a new vector with X, Y, and Z values. X and Y are in the map plane. X and Z are in the map plane, and Y is our height map. It's setting the UVs that the textures are going to map on. This is vector 2 of the X and Y scaled by the width and height. So those go from 0 to 1. And finally, we have to add the triangles. Each of these little squares that we're making is composed of two triangles. So we have two add triangles here for index width plus 1, and index width plus 1, index and index width, and index plus 1. Those are the four corners of my triangle, of my rectangle, divided into two triangles. And I return the mesh data. Another tiny piece is the map display. This is a mono behavior. It's added to our map generator. It has public functions for displaying the texture or the mesh data. It can draw the texture or draw the mesh. And that's pretty simple and straightforward. We're just using shared materials. By the way, shared materials differ from materials in that when we modify a material, it only modifies the material attached to the specific renderer, whereas a shared material will modify the material of any object that uses that material, similar for a shared mesh. This is pretty much Sebastian's tutorial as far as episode 5. He hadn't yet said how to save the results of the generation. Making all this stuff is nice, but if you can't save it, what use is it? So I skipped ahead and looked and found this routine for a mesh saver, and cooked up this little thing with a button, save mesh as a new instance. It finds the mesh. It's a shared mesh. It has a save mesh function. This is the save mesh function, which takes all that as arguments, some Booleans that are both true. These are we have to have a path that gets a relative path. This is going to save it into our project folder. There's an optimized mesh thing, whether we optimize the mesh. But finally, we use the asset database, create asset mesh to save, and where we want it to go, and we save the assets. The texture is saved in a similar way. It's actually the same program, just adapted to put a texture away instead of a mesh. Once you've got this texture, you're going to have to make a material that you can then apply to the saved mesh that you've generated. So all pretty cool, and it generates terrains. Of course, if I run this, it generates the terrain, and we just have a static camera and we're looking at it. Over here are some scenes where I've, don't save, are some terrains that were generated, and we can walk around on them. They're just regular meshes, and they have mesh colliders on them. You have to add that yourself, but that's all pretty cool. So I'll stop sharing at this point, and I'll stop recording, and I'll see you all in class. Bye.